This is going to be awesome. I'm glad you're here. All right, so would you like to know how to solve question 6?
Yeah.
Well, I'm going to show you how to attempt a problem like this, but then I'm actually going to give you a sketch of how the most awesome way to prove it is. Say it was just me doing this, right? Doing a problem like this. And if you look at a problem like this and it's really hard, we know the setup. If you don't have any idea, you've just got to plug in numbers, all right? You've just got to put in the grunt work. You've got 90 minutes. May as well use it. We've got a squared plus b squared on ab plus 1. The problem with an equation like this is that somehow there has to be a proof, okay? And it is totally mysterious at the moment what it could be. So what you want is to actually look at what answers, the suitable answers, what they actually look like.
You just want to see the machine working before you think about taking it apart and looking at how it works.
Yes, but I want to see the machine producing this thing, because if it produces a fraction, it's really nothing to me, okay? But if it produces a whole number, I want to see if that's going to give me some insight. So I'm going to try putting in a equals 1, b equals 2. It's safe, they're small numbers. So if we plug them in, we'll get 1 times 2 plus 1. So that means we're going to get 5 on 2.
Is that right?
Sorry, no, it's right. You're 3. Yep, went too fast there.
Cool.
So basically it was 1 times 2, 2 plus 1. Yep, yeah, that's right. Okay, thanks for that help.
That's a point for Brady.
Yeah, it is.
Brady on the Maths Olympiad.
But also it's, who cares? It didn't really tell me anything. So I'm going to try something else. Maybe, let's try something else. Okay, maybe I'll go a equals 0, b equals 2. All right, remember we can choose 0. So now let's throw them in. So we get 0 squared on 2 squared, 0 times 2 plus 1. This is looking promising. So that means it's now 2 squared over 1, or 2 squared. And I'm not even going to work out what 2 squared is, because it's actually in the form I want it. Now 0 and 2 actually produce a whole number which is equal to 4, but more importantly it's a square number.
All right.
What's great about this is if I have a look at the way this is actually happened, if you have a look at the bottom line there, it's 0 times 2, 0 squared plus 2 squared. It didn't have to be 2. I mean that would work for 3. You have 3 squared and 0 times 3. 0 down there is going to wipe out whatever's there, it just leaves the 1 on the bottom. So 0 times 3, 0, 0, 4, 0, 5, 0. So in actual fact, I found an infinite number of solutions. I've got 0, 1, 0, 2, 0, 3, 0, 4, and I already know that they're going to produce 1 squared, and that one there is going to be 2 squared, this one's going to produce 3 squared, this is going to produce 4 squared. So there you go, pretty good, huh?
All right, so we know every square number will fall out of this equation.
Yeah, but not only that, I found infinitely many solutions. I mean, that's pretty cool, isn't it? The only problem is that's not enough. Even having infinitely many solutions isn't enough. If a pair of integers are thrown in there and somehow it was like a number like 30, that's not a square number, and then you haven't proved what you need to prove. The other thing is they're telling you this is the case. So this is when it gets really hard, when you have this realization. And the smarter you are, the quicker you actually realize this. It's actually at this point you hear something laughing in the distance. And it's the problem, it's laughing at you. Because it knows something and it's not telling you. Anyway, so now we've got to try and do something else. And now the problem is that if you don't have any ideas, you are forced to just do grunt work. I'm going to quickly do that here actually. I'm just going to put in like a matrix. I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8. So these are my A's. And I'm going to go down. I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8. Now I'm going to start plugging in these numbers, and here will be the result of this. Can I just emphasize, I have no reason to expect this will work. But if you don't have any ideas, and if you can't do the algebra and playing around with algebra, sometimes this is what you're resorting to do. So first of all, these are all good. So this one here produces 0, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared. So blue means a winner. We've already found them. So 0, 1, 0, 2.
Yep.
Okay. And we also have 1, 1 is a winner as well. All right, so I only have to populate a diagonal because like we're repeating here. So I'm going to quickly work out these fractions. And so just imagine under exam conditions what you need to do here. So you need to kind of look at these things and you go, yeah, okay, that's no good there. Oh geez Louise, this is pretty hard. So you know your emotions might be going up and down at this point. You're sort of sweating. You know you're playing for your country here. What's happening? Whoa! Hang on, it's 8, 2. Is that right? Did I get 4? I think it is. I think it's 4. Hang on, I have to write it again. 4. Hang on. Yep. That is. Yep. We found another one. So after all that, after doing all these calculations and getting nothing, we got an answer. We got an answer with 2 and 8. So now the question is why? So let's actually throw it in there. So if we actually put in 2 squared, well, the thing to realise here is that 8 is 2 cubed, yeah? So now if we put in 2 cubed there, and then we have 2 times 2 cubed plus 1. So if we do a little bit of algebra, we end up finding that this gets to be 1 plus 2 to the 4, and the bottom is 2 to the 4 plus 1. So that actually cancels with that, and we get a secret solution. So now we've found 2 and 2 cubed also generate another whole number, and it's a square, right? But just like before, we used 2's here, but it actually will work the same. You could run the same logic with 3's or 4's, 5's, any numbers whatsoever, whole numbers. So we've just found another infinite number of solutions. We've got 2 and 2 cubed will generate 2 squared, and we have 3 and 3 cubed will generate 3 squared, and 4 cubed. So really, this is amazing. So in actual fact, we found another infinite number of solutions, and it took us a lot of effort, so now we feel confident we've got all of them, except we haven't. And this is the genius of this problem, is that there is a VIP super solution, which you have to be very clever to find out. Okay, do you want to see it?
Yes.
This is the reason why this problem is so hard, because not only you doing grunt work is going to help you get to the secret solution. The amazing secret solution to solving this problem is actually a beautiful piece of observation. It is, and I'm going to show it to you right now. What the people who solved it realized was that out of the solutions that were semi-easy to find, there were kind of groupings together of answers that were the same. So 0 and 2 produced 4, and so did 2 and 2 cubed, right? And 0 and 3 produced 3 squared, etc., right? So the very smartest of the people that actually were able to solve this problem kind of worked out, I wonder what the connection between these pairs are, right? So what they did was they actually looked at this equation. So they looked at the equation which is a squared plus b squared. They looked at the equation for a squared plus b squared on ab plus 1. And they looked at it just for one of those solutions. So I'm going to choose 4. And so now what they did was they actually graphed. They graphed the solution. So here we've got A and here we've got B. Okay, so now they looked at the 2 solutions they had. 0 and 2. If you stuck that in there, you get 4. So that's a solution, 0 and 2. And also 2 and 8 were another solution. That gave you the 4. So that means that we could draw a graph. So let's do it like this. So if we say A equals, what is that? A equals 0 and B equals 2. Okay. All right. Okay, so there's that solution there. And then we know another solution is at 2, 8. So that's A equals 2 and B equals 8. So that's up there. And then, you know, you kind of like draw your graph like this, and you kind of like draw a graph that goes like this, and it actually cuts through here. So now, if we did this on like grid paper, we're only interested where this actually intersects the grid, because it's like where it's a whole number and a whole number. But what's amazing at this point here, this is 0, 2, and this is 2, 8. There's actually 2 more solutions that we haven't included. And this is the most beautiful thing about this problem, is it actually comes down to a simple observation. If we look at this equation here, if we swapped around A for B, what would we get? Well, if we write, instead of A, we write B, and instead of B, we write A, and instead of A, we write B, and that equation is the same.
Yeah.
It's just rearranged. You can't always do that. Some equations, if you move around the variables, it changes it. But in this case, you move them around, it looks the same. So that means we've actually got two more solutions. 0, 2, there's also 2, 0. So there's actually a solution there. And there's also another solution at 2, 8. And really, to draw this graph properly, it actually splits in two. Something I didn't realize when I first looked at it. So now this is nuts, because these two lines represent this one equation. So what does that mean? Well, it means if we actually look at 2, I haven't lined this up properly here, but this is supposed to be for A equals 2. There's actually two solutions. For A equals 2, B equals 0, and B equals 8. So we've actually found a link between both solutions. So if we actually look at this problem from underneath, so what's actually going on here is that if you actually work out, if you actually solve this equation for just A equals 2, effectively what's going on is that you're actually looking at the equation expanded into the third dimension here, and you actually get a shape that looks like this. So he's actually worked out, this is actually supposed to represent a parabola. It's actually a quadratic equation. So the people that worked it out, in actual fact, worked out that these two solutions that were found independently actually have a wormhole connecting the two, which involves a quadratic equation. And so what they're able to do then is they're able to actually link every single answer by drawing parallel lines. So this comes up here and in actual fact intersects it here, and this goes off and shoots off and hits the graph again and intersects it again at another time, but at a different number that we didn't find before. It's actually 8 and 30. And so you can actually do what's called Vieta jumping. You basically jump between these two curves at right angles, and you find a secret, super secret, hidden, infinite column of solutions. And basically, for any solution here, he basically worked out the connection between all solutions for a given whole number.
So this is a curve.
This
is a curve.
Yeah.
And you just draw this sort of like
Yeah.
a staircase.
That's right, and they're all connected by parabolas pointing at right angles underneath, and they're going off at right angles. So it's really, I think, one of the only times that research mathematics or something meaningful has come out of a maths problem from an Olympics, because Vieta jumping is now something that you get taught. I mean, this is a game changer, really. It's like a Frosby flop in high jump. But it's amazing because it's such a beautiful solution.
So the West German person who submitted the problem didn't know about Vieta jumping?
No, he did. But the guy who solved it amazingly used Vieta jumping in just this sleight of hand and solved it in a paragraph.
Well, you've watched for this long, so let me give you a little postscript. We mentioned that Terry Tao, the future Fields medalist, only scored 1 out of 7 on this notorious question 6 from 1988. That, of course, is with a caveat. He was attempting the question the day before his 13th birthday, and he still went on to become the competition's youngest ever gold medalist. And in fact, only 11 out of the 268 contestants at the Olympiad managed to completely conquer this question. One of them was actually another future Fields medalist, Nobao Chow, who actually got 42 out of 42 for the whole exam. But a third future Fields medalist in the room, Eilond Lindenstrauss, also scored only 1 point on question 6 on his way to a bronze medal. The boy who we mentioned receiving a special prize for his ingenious solution is right here, Emanuel Atanasov from Bulgaria. He picked up an overall silver medal. But do you know who else got the full 7 points for question 6? That girl there. That's Svetoslina Stankova, also from Bulgaria, who won a silver medal in the Olympiad. And if that name rings a bell, it's because Svetoslina, or Zvezda as we call her, is a regular contributor here on Number File. And if you like, you can go right now and watch some more of her videos.
It comes from my own textbook, which was associated with the math circle in Bulgaria. It is called Mathematical Olympiads, and it was published in 1985. So the actual problem is the following.
A ruler, right? I'm able to show you how beautiful, how simple it is now to interpret this problem. This big circle here, Brady, this big circle here, what does it invert to? Well, first of all, it passes through the center of inversion.